Before we start, just wanted to ask, do you hear me well? I mean, like, because Zoom writes me something, odd.
Yes, we can hear you.
Yeah, fine. Then we can start. Okay, so we begin the second part of the course, right? So you can safely now forget the first part, so it won't be asking any of the midterms or the exam. And actually, today's lecture is not a typical one, so it's not a model of something, and it won't be directly midterm or exam relevant. So it's just a collection of some reminders and also some particular mathematical features of some object that we will use in further models. So it's a technical lecture, but I also want to say you can be safe that nothing of like exactly these things won't be relevant for you, but it's just a formal reminder of objects that we will need to use. So I probably believe that some of you are familiar with some math that we will study today, but I don't know. I mean, like some can be not familiar. And then yeah, probably this second part is the toughest one. And I had a choice actually which part to be the second and which to be the third, and I decided that the toughest one will be the second because you have a less weight on the second midterms and on the exam. And okay, I mean, like if even if you don't understand it well, you won't lose too much. And also, for some who studied it, it will be a reminder of exact things that will be relevant for the course. And the plan for today, I mean, like the exact thing that we will cover is the following. So we'll cover dynamic programming. So it's Bellman equation in two variants. So it will be in discrete time and in continuous time because, they both have some specific features and we will have both types of them. So first we'll study some discrete time model, and then we'll move to continuous time. And for continuous time, exactly, we will need two stochastic processes, which are called Poisson process and Brownian motion. It's not that, they are the most important or whatever, but they are the most convenient actually for economic modeling. And so, as in theory models where you do not have any kind of specific assumptions for the processes, they are used extensively, and also they are quite relevant for the real world. So for instance, Brownian motions or their analogs in discrete times like random walks, they're used in financial markets to model price movements or whatever. And Poisson processes, they are more like, okay, they're also important, let us say it this way. So we'll begin with dynamic programming, and first we'll do it in discrete time, and then we'll move to continuous time. So the basic idea of dynamic programming is not very deep. And for instance, I have a math background. So, I didn't study economics for my first education. And this topic is actually pure math, right? And in math, you do not study this stuff. So when I studied economics, I faced it for the first time, actually. And when you face it for the first time as a mathematician, you do not see anything deep in it. But it turns out that, with years, I now understand that, sometimes it can simplify life quite mysteriously. So the idea as promised is not very deep. So you can take first a very standard math problem where you need to calculate an infinite sum, right? So it's a power sum. So first is like you take some numerical value a from 0 to 1, let's say 1/3, right? And you need to calculate the sum of its powers. So it's basically a to the power of 0, which is always 1, irrespective of a, And then it's a to the power of 1, a to the power of 2, a to the power of k, and so on. So you need to calculate this infinite sum. I believe you all can do this, but when you first face this problem, it's school or whatever, the original problem of this task is that you cannot calculate infinite sums, right? Naturally, because they're infinite, right? You need to perform infinite number of additions. And you no matter how fast you can do addition, it's not feasible to do infinitely many. And you can calculate a plus 1 plus a, 1 plus a plus I squared, and so on. You can calculate any finite sum, right? But how can you calculate an infinite sum? And then you just, the basic idea to solve this problem is to reduce this infinite sum to some kind of finite problem, right? And actually, as I believe, again, you all know what you do. You denote this sum as sum s, right, which is unknown to you. And then you can write that s, which is this sum, is equal to 1 plus, then you take a from this sum, right? And by what you multiply is again 1 plus a plus and so on. So because it's infinite, right, it's again s. And you can solve this equation eventually and derive as the fact that s is equal to 1 divided by 1 minus a, right? So what did you do? You just transformed an infinite sum into a finite equation, right? And this dynamic programming basically does the same. Because in all our models that we will have infinite horizon, right? So you need to choose the optimal strategy up to infinity, and therefore each choice, it affects your instantaneous utility, right? So eventually what you maximize is an infinite sum of your utilities, right? We will have more complicated problems, of course, because there will be some potentially, kind of state variables, uncertainty, whatever. So it won't be just, a sum of known numbers eventually, but in any case, it will be an infinite sum, right? Which again, we cannot calculate normally. And what we'll do exactly this, right? So we will represent our current sum, right? This, how we'll call it, value function, as just instantaneous, right, gain plus some multiplier times, again, something close to the original value function, right? To the original sum, right? So we'll transform it into this way. And this will help us actually to calculate the needed either value function like this as, or, some optimal actions, which is called policy function, if I remember correctly, right? So in any case, it will be quite close to this. So let us move directly to the problem. I will use terminology which is close to macro, actually, right? I don't know, probably I believe in the third and the fourth year, you have studied macro, at least to some extent. And this is the most basic macro problem for you, probably. It's a Ramsey model. But we'll have it as an example for both discrete time and continuous time. And so in my annotations for the general problem, I will follow basically this Ramsey model example. So we'll assume first, as promised, the time will be discrete, right? So time will be from 1, 2, and so on, up to t and so on. And there will be one agent, right? And this agent has utility function, which depends on two variables. So it depends on consumption today, right? Which I denoted as C. And it depends on the state variable. So it's like conditions, right? And in all our models, we will have this kind of consumption, right? Something that you choose, right? So we'll call consumption as choice variable. And in all our models, we will have it as just a scalar. In more general frameworks, you can have that your choice variables, you can choose multiple dimensions, right? In multiple dimensions. And therefore, it won't be just a scalar that you choose, but it can be a vector that you choose. In all our models, we try to be simple. And so your choice variable or your consumption will be just, a scalar that you choose. And ST in standard Ramsey model is kind of savings, right? So like your budget for the future. But in general, it's just state, right? Conditions in which you are. And again, we will call it state variable. So something that describes your state, basically, right? Something that that determines your decision in terms of consumption, right? And again, in our models, it will be just a scalar, right? So in Ramsey model, as I said, it's just savings, right? So the amount of money at your account. So this terminology is pretty standard. So all variables which are relevant for your utility will be divided into two categories. Choice variable, something that you can choose, right, at each moment, and they directly then affect your utility, and state variables, something that you cannot choose, basically, right? But they are relevant for your utility. And how do they relate? They are related this way. So like a standard example, right? You have some fixed budget for a month with your salary, let's say, and clearly, the more you spend today, right, the less savings you will have tomorrow, right? And therefore, we assume that the state variables, it changes depending on your choice, on which choice variable you chose, right? So if we assume that at period t, you chose some consumption CT, right? And it was in state ST. So basically you had some savings ST and you decided to spend CT out of them, right? Then we will assume that it results in some savings ST plus 1 in period T plus 1, right? So here, as I wrote it, it's kind of a deterministic relation, right? So as arguments, you have your savings for today and your consumption today. And as an output, you receive your savings from tomorrow, right? In more advanced models, and we will actually have them, this dependence can be stochastic, right? Because, not always, you know for sure your budget for tomorrow. Occasionally, you can have some, liabilities or whatever, unexpected returns from some whatever, right? So sometimes these dependence can be stochastic, but this doesn't change the main idea. So in general, there's just some relation. That is, your choices today affect your state variables tomorrow. Right? That's the main thing that you need to incur from. And the agent's goal is to find an optimal sequence of actions. Right here, I say that these CTs are actions because you can choose these CTs. And what is important, right? Here it's written quite, in complicated language, but again, with this particular example, when you have some budget for a month and you just need to choose consumption optimally, right? For instance, you have a natural constraint, right? You cannot spend more than you have. Of course, you can, take a loan from a bank, whatever, but let's assume it's not the case, right? And the natural constraint will be that, your choices are somehow limited, right? You cannot spend more than you earn. And therefore, naturally, your state variables, they determine the set of possible consumptions, right, for this current period. And this is summarized here, right? So that I just wrote that consumption today, it depends to some set which depends on the state variable today. Like A is for admissible, right? So it's like possible consumptions when you have state ST, right? And among these admissible consumptions, you need to choose an optimal sequence such that it maximizes your discounted sum of utilities. So that's your basic goal here, right? You always want to maximize the discounted sum of utilities under the assumption that your choices today affect the state tomorrow. So that's the basic problem. Do you have any questions regarding the statement of this problem? Okay, so let us transform again as promised. So here it was a statement, right? And again, as we've seen in the basic example, it's an infinite sum, right? Here it's more complicated. It's not a sum of just fixed numbers, right? Because this utility can change according to some specific law of motion, how it's called for the state variable. So it's more advanced, but in any case, it's an infinite sum here, right? And remember the basic principle of like, the first step in this whole sequence for solution is just to transform this infinite sum into an equation, right? In a finite object that we can deal with. And how do we do this? We'll introduce what is called the value function. Value function is basically an analog of this S, right? So, but here is one specific feature, right? So when we introduce a value function, it's not just a like, this infinite sum. It's a sum when you make your decisions optimal, right? Because when you just take some C's, right? When you just take them arbitrarily, it results into some accumulated utility, right? When you take another stream of cities, it results in some other utility, right? And your goal is actually to find an optimal sequence of C's, right? And exactly for the value function, we denote the numerical value for your accumulated utilities that you get when you choose these CTs optimally, right? So because of that, we will have these stars here, meaning that these C's are optimal here. And also, we need the value function to be defined for all states, right? Because you can have savings 0.4, 0.5, 0.7, whatever, right? You can have any numerical savings, and we need to introduce the value function for any argument of savings, right? Remember that in any point in time, the only thing that you know about yourself is ST, right? The state in which you are. And in this state, you need to choose CT, and then it, according to this law of motion, you receive utility CT-ST, right? And move to the state ST plus 1. Right? And again, in this state ST plus 1, you need to decide on CT plus 1. Then you incur this utility and move to CT plus 2 and so on. Right? So what is important for us is to define this value function for any ST, right? For any numerical value of ST. And how do we do this is exactly this, right? So here it's kind of, it can be done in various ways. So what did I do here is when you are at state ST, right, it implicitly means that you're already at period T, right? And right now you need to choose CT, right? And therefore, from today's perspective, your first utility that you will get will be U of CT star ST, right? And if you look here, this enumerator variable is tau, right? And it starts with T. And if you substitute exactly T, you will have here it's 0, so it's 1, right? And here it's exactly CT star and ST, right? So exactly the first utility is promised, right? And then for all future periods, right, you start to discount them with beta, then with beta square, and so on. So the value function for state variable st is defined in like current terms, right? When you're already at period t, right, and when you are to choose ct and then carry first utility, and then you start discount. So what is important basically, right, is like from which point in time you evaluate the utility, right? Because if you start to evaluate your utility at period t from period 1, let's say, right, you need to discount it by beta to the time of t minus 1, right? So it's all about discount, right? So here your value is defined in like current terms, right? So whenever you have state variable st, right, it implicitly means that you're already at period t, and you discount the future exactly from t, but now not from the very start, right? Is this point clear? I mean, like it's quite trivial, but you know, you have some kind of choice here how to define value function, and I decided to define the value function in like current terms. Right? Okay. In any case, even if you don't understand, you can just assume it's a definition and don't care about it. And again, just to remind you, we understand the value function, right, is a numerical value that you gain from an optimal choice of CT from now onwards, right? So it's in state ST, and first you choose CT, right, and then CT plus 1, CT plus 2, and so on, right? And we assume that if you choose them optimally, this gives you exactly this value of ST, right? So it's not just, you know, some stream of consumptions. No, it's an optimal stream of consumption that gives you the value function. And using this value function, right, here it's absolutely the same as it's in the previous slide, no cheating here. Then using this value function, we can construct what is called Bellman equation, right? We can basically relate today's value, right, and tomorrow's value. Again, basically, it's quite close to what we did in the very original example, right, with S. Here, you know, because you have additionally the law of motion for the state variable, it's not exactly the same as, right, but it's still comparatively close. So how does the Bellman equation looks like? So let us look at this value function. So let us decompose it into two terms, right, in this sum. The first term is the very first term, actually, right? It's exactly u of ct and st, right? So here, when you have tau equal to t, here it's 1, right? And the first term is actually this one. And then the second term is beta, right? Times u of ct plus 1 st plus 1, and so on, right? So again, as in this example with an infinite sum, what we did, we just plug out beta from the second and all other terms in this infinite sum. And what do we get? Because we, in this value function, we act optimally, right? Because if you act optimally from period t onwards, it means that you act optimally from period t plus 1 to infinity as well, right? Because, you know, it's always optimal. And therefore, this second term here will be exactly beta, right, times the value function. And the value function here, the argument will be exactly st plus 1, right? Here I specifically write st plus 1 as a function of ct, right? Because also, I mean, like it's, I will correct, it's kind of, you know, here it will be more correct to write as here as it's a function of ct and st as well. So additionally here I will add st. But what is important is that, you know, ct itself, right, the one that you choose exactly at time t will be relevant for how st plus 1 looks like. So that's exactly to underline this thing. And eventually, right, here you will start with st plus 1, right? And here it's your instantaneous utility. And remember that you act optimally, right, in particular at period t as well. And therefore, your value function, right, from today is basically the sum of these two when you choose ct, right, optimal. So all in all, it's just like that. Your value function can be decomposed into your today's instantaneous utility and your utilities from tomorrow onwards, right? And when you choose about your consumption today, you have basically a trade-off, right? Between today's instantaneous utility and because your choice of CT, it affects ST plus 1, right? So it affects the state variable with which you will be from tomorrow onwards, right? So it somehow affects the value function that you will receive tomorrow, right? And that's basically what is called the Bellman equation, right? So it's not very deep, right? You just write that when you behave optimally, right? It's basically represented that you just take your choice optimally in such a way that it maximizes the weighted sum between your instantaneous utility and you know, all future utilities, right? Because it affects the state variable with which you will start from tomorrow. Any questions regarding this? So the first step is basically done, right? So we had an infinite sum initially, and we managed to transform it into like a finite equation. But, you know, again, as I told you, when you first see it, I believe, you know, you see it not for the first time, but whenever I personally first saw it, it wasn't really clear like why it's an improvement at all, you know, in comparison to the original formulation, because, okay, we managed to do, you know, kind of a finite equation here, but what is, you know, tough about that is that you have max sign here, right? So you need, it's not like equation, you need to have maximizers here. And also, you know, here you have st, right? You have the same value function, which is nice in both ends. And this utility is something exogenously given, so it's known for you. So it's fine. But what is tough is that the arguments here and here, right, are different. So it's not an equation for some particular function, right? It's what is called a difference equation, right? When in the same equation, you have the same function, but with different arguments, right? So it's like basically f evaluated at 0.5, and in the right-hand side, you have f evaluated 0.10. In, you know, math still doesn't have like a general procedure on how to solve this equation. I mean, like, in some limited ways you can do this, but it's very limited. So all in all, at this point, you know, it doesn't look very promising. And actually, eventually, as we will see in some models, you can be just lucky, you know, and eventually we'll be able to solve it. But, you know, for a generic problem, you know, there is not much hope that you will be able to solve it in closed term. So most of the time you can solve it numerically by just approximating, you know, some value function from the distant future and then going backwards. But all in all, you know, don't be tempted to say that it always works. No, it works only in limited amounts of models, and where it works, that the model is good and we will have it, but in most of them it doesn't. So let us consider a particular example, right? As promised, it's just the Ramsey model. It's not directly, relevant for your midterm. It's just an example, right? Okay. So don't try to memorize all these steps. In any case, they will be relevant. So the basic example here is that your utility is, let's say, it's natural logarithm of CT. So, here in our general formulation, we allowed that your utility today, it depends on both your exact consumption, choice variable, and also on your savings, right? State variable. For most problems, we will have that your instantaneous utility depends only on your choice variable, which is it in Ramsey model. So it depends only on your consumption, but not exactly how much money you owe, right, at this particular moment. And the evolution of the state variable, basically your saving is like that. So when you decided to spend CT on your consumption today, remember that your savings were ST, then you subtract CT. So then that is your leftover in terms of money. And we assume that, you have a bank account. In economics, everyone has a bank account. So, and your money each day, it grows at a percentage R. So if your leftover was like that, then you went to a bank, loan them to them, and they returned you exactly the same plus some R percentage. So R is particularly small, right? But still it exists in small. And that's exactly your disposable savings for the next period. So for this particular problem, that is what is called the law of motion for the state variable, given your choice. Right? Then again, we have the general way to write a Bellman equation, and let us just substitute everything that we know for this particular example into a Bellman equation, right? So in your instantaneous utility is log of CT, right? Here it's beta, and here it's the value function of st plus 1, right? And st plus 1 here is exactly this, so I just decided to substitute it here. So that's exactly why I wrote CT here, to underline the fact that your state tomorrow depends on your consumption today, right? So exactly, it means that CT enters here, right? So here a particular feature of this model is that your choice variable CT is a continuous variable, right? So your consumption can be whatever, right? Actually, in our models, we will have discrete variables as your choice variables, and I will have a separate slide for discussing it. But in this particular way, particular problem, it's simple, right? You have a continuous variable, and therefore, what you do, as a natural way to proceed with solving this problem would be just, you have to just maximize this sum with respect to CT. And therefore, you just, write the first order condition, right? And actually, what does it give you? Like you differentiate this, it will be 1 divided by CT. And here you differentiate this with respect to CT, right? It will be beta here, 1 plus R from here, and minus 1, right? Therefore, I kind of equate to two parts, right? And also you differentiate the value function itself, right? And then to write it more compactly, I decide not to write the same expression as the argument here, but to write st plus 1. So the first order condition is like that. So if you take a look at the left-hand side, we have CT, here we have constants, right? So at this stage, it looks like quite good, right? Our goal, remember, is to find optimal CT, right? But what is not good, we have the value function here. We have really no clue how this value function looks like. And the value function, you should always remember, it's an auxiliary object. We are not interested in finding the value functions, right? They are needed just to convenience, just to write this equation, right? Eventually, and on our way to solve, we can find the value, how the value function looks like. But what eventually we need to do, we need to find an optimal sequence of actions, right? You should never forget that. And here we almost have it, but we have some kind of derivative of a value function, which we have no clue how it looks. Then I should also notice that there is no general way how to solve a Bellman equation. So you have it here, like the very natural way is to take first order conditions, and then, you know, it's a wild west. You can do whatever you want, basically. And for this particular model, you can kind of solve it eventually. But again, just it's not a general algorithm of how to do this. You do it as you want, as you can, basically. So for this particular problem, just, you know, to at least show you how it can be solved, what you do is you apply envelope theorem, right? Envelope theorems are applied exactly to these kind of scenarios where you have that one function is equal to the maximum over some other variable of some expression, right? And then it states that if you take the derivative of the function from the left-hand side, here clearly this optimal CT, right? Your optimal consumption today clearly depends on ST, right? On your savings today, right? So when you just differentiate the right-hand side with respect to ST, like naturally you would like to account for the dependence between CT and ST, right? So because CT is actually a function of ST. But the envelope theorem just says you can ignore this dependence, right? And do not differentiate CT with respect to ST, and differentiate this whole function basically as a function of ST. And then after all the differentiation, you then substitute back the fact that CT, you kind of remind yourself that CT was a function of ST, right? But only after that. And actually, let us apply this envelope theorem. So we differentiate with respect to ST. The left-hand side is trivial. The right-hand side, actually, this is 0, right? Here again, it's beta 1 plus R minus 1, and therefore it's, no, sorry. We differentiate with respect to ST. So it's beta 1 plus R. Here it's 1, right? And then we prime of, again, for compactness, I wrote ST plus 1. So eventually we have these two equations. And if you look at the first one, right, you can see that the multiplication of V prime of ST plus 1 and CT is some fixed constant, right? So no matter what time index you have, the multiplication will give you 1 divided by beta divided by 1 plus R, right? So irrespective of T. And let us use it and write it in some form, right? So we can actually exchange the time index, right? So that we can plug in T minus 1 instead of T, right? And have additionally this constraint, this equality, right? And then let us divide these two equalities, right? And what we will eventually get is this, right? Basically, as promised, it's a multiplication between CT and V prime ST plus 1, right? Doesn't depend on the time index, right? So what is important is that consumption at period something multiplied by V prime of S at period something plus 1 is the same, right? So that's what we can get from this. And also from the envelope theorem, let us again divide these V primes, right? And eventually we'll have that this division is equal to beta multiplied by 1. And let us exclude finally these value functions. And what we will eventually get is that CT, as you see here, right, is equal to this number multiplied by CT minus 1, right? I won't solve the problem later, like for later stages, because I believe you should know how to do this. I can briefly outline that you just take this kind of equality between states, right, and compose an infinite sum of STs, right, discounted infinite sum, and basically just write that the sum of like CT plus 1, CT plus 2, and so on, discounted by a fixed number, it should be equal to some fixed number actually, right? And then you substitute this dependence between consecutive consumptions, and actually you will be able to find each consumption. But again, this is quite irrelevant. What is important for us is that we managed to kind of obtain an equality for our choice variables purely and manage to exclude the value function, right? Because remember, we use the value function, but we don't like value functions, right? The auxiliary object, right? They manage to kind of simplify the notations here, right? Because it managed to reduce our problem to just one equation. But again, eventually we just need our choice variables, equations on them, but not the value function. And eventually, in this particular problem, we managed to obtain an equality purely for the choice variables, which is really good. And then how you exploit this found condition, right? It's up to you. Here, it turns out that you can, using this condition, find the optimal stream of consumptions. Any questions regarding this particular example? Okay. So one minor comment about the model that we will have. Actually, what we will have, and I noticed it, not that long a time ago, is that, okay, I have these kind of preliminaries, but in the model that we will have, we'll always have binary choice variables, right? So here it was a continuous choice variable CT. And for that, we just took first order condition, right? So we differentiated this inner part with respect to CT. In our problems, we will have not just discrete like choice variable, but even binary choice variable, right? And for that, you kind of differentiate, right? You kind of differentiate with respect to discrete variable. And actually, we will see that, the algorithm of solving will be slightly different, but, in some parts it will be more complicated even, but the natural way how to do this in these particular cases is that you just assume that this particular choice first, like out of two possible, is optimal. And then you kind of have a fixed Bellman equation, right? You just substitute a particular CT basically, right? And it gives you like not an equation with maximum, right? It gives you just exact equation. And you solve this exact equation like in closed form if it's possible, right? And in our models, it will be possible. And therefore, it will mean that for this particular choice, when it's optimal, your value function is like that. You will be able to find it in closed form. And then you substitute another possibility for CT basically, right? And then again, you do the same and you solve the new Bellman equation, and it gives you another value function. And therefore, you will basically have that for a region where one action is optimal, you have a value function. And for another region where something else is optimal, you have another value function. And like at the final stage, you will need to just somehow glue this value function, right? So you will need to connect these separate value functions into one global value function. And this algorithm of how you actually glue these two value function is kind of, is a tricky thing, and we will go through it. So that's it about discrete dynamic programming. So next we'll move to continuous time. And continuous time is more widely used now in economics, purely for convenience. Actually, as I noted before, right, in discrete time, when you have a Bellman equation, you have what is called difference equation, right? Because at the left-hand side, you have the value function evaluated at some particular point, and at the right-hand side, you have the same value function, but evaluated at different points. And that's a functional equation for the same function, but evaluated at 2 different points. And that's generally very rarely solvable. In continuous time, why it's better in this respect? Because in continuous time, from today to tomorrow, there is there's actually no tomorrow, but it's the next instant in some sense, right? And the next instance is very close. And therefore, because the next instance is very close, your state variable won't change too much, right? And therefore, the argument for the value function at the right-hand side won't change much, right? It will change only infinitesimally by the infinitesimally small argument, right? Because the time increment between today and the next instant is infinitesimally small. And this will allow us to use the Taylor approximation, right, for the value function at the right-hand side. And if you have basically the same state variable as it was before, plus some marginal change in the state variable, right, you will apply the Taylor rule. And what it will give you, it will give you the same value function evaluated at the same state as in the left-hand side, plus like the derivative of this value function, right, evaluated again at the current state variable multiplied by the change in the state variable, right? It's a Taylor rule up to the first order approximation. Right? And actually, eventually, this value function of the current state, they will cancel out. What you will eventually get will be a differential equation on the value function. And differential equations are much, much easier to solve than difference equation because there is much richer theory on how to solve differential equations. And therefore, dynamic models in continuous time are more widespread now because there are just more chances to solve them in closed form. So let us generalize our, construction from the discrete time to continuous time. So before we had like a state variable at time period t, and next it will be state variable at t plus 1. Now we will divide our time into small increments. So it will be like we are still operating in discrete time, but with very small time increments. And this time increment will be denoted as dt, right? And we will still assume it's strictly positive, right? It's not 0. It's kind of epsilon from, calculus. So it's something small, but not exactly 0, right? And when you finally need it, you can kind of, approach it to 0, taking the limits and everything like that. But until the very last moment, you always assume it's something small and positive. So instead of, in discrete time, we had today, right, and tomorrow, kind of t and t plus 1. And now in continuous time, it will be kind of today, time period t, and tomorrow, in our understanding, will be t plus dt, right? So it will be like that. And also, it's kind of, a strange world sometimes. You have to get used to it, but I'll help you in all the problems. So don't expect anything cruel with you. But, kind of a mnemonic rule, the rule of thumb that you can use is, we will need only first order approximations for everything, right? And therefore, once you will have dt squared, in some expression, actually it can arise somehow, right? Because dt, it participates in some formulas. So occasionally, sometimes you can have an expression dt squared, right? And dt is strictly larger than 0, but dt squared is 0, right? It looks kind of odd and against any logic, but it's like that, right? Actually, you can make everything rigorous. So you need to just have first order approximation, like first order approximations of everything, and then you take the limit, and only the terms of first order of infinitesimally small, they make some impact, and higher orders they actually approach 0. But it's much easier to just kind of use this rule that everything, every expression that depends on dt, if you need a Taylor rule approximation out of it, you just need to take the first order approximation, and that's it. You shouldn't care about higher orders, because according to our rule, dt squared is equal to 0. So let us try to master it into the same Ramsey model, but now we'll have continuous time. So again, the utility function will be the same ct, right? And now let us outline the evolution of the state variable, the law of motion, right? Here you just need kind of to free your mind a bit and to see how it goes with these small time increments. So again, assume that your current available budget as ST, right? And today, right, in this instant, you decided to have consumption of CT, right? Remember now that it's kind of continuous time, and time increment is dt. So within this dt, you basically consume CT in each instant, right? So your total consumption will be CT times dt. Before dt was equal to 1, right? So basically it was just minus CT. Now, it's like the smaller is the time period in which you consume CT, the less you consume in aggregate terms, right? So your total consumption within this infinitesimally small period of time is CT times dt. Then in continuous time, you also have slightly different discounting, right? And vice versa growth rates. Because remember, when you have in continuous time, it's like e to the power of minus RT, for instance, when you have discount, right? And whenever you have that you loan this sum to the bank, right, and it grows at percentage rate R, right, then the eventual gains will be e to the power of R dt. Because here, again, you loan it to just a period of time of dt, right? And that's exactly the growth rate, right? Because you can see here, right, when dt is small, this is approximately 0, it's approximately 1. And for instance, also up to the first term, it will be just 1 plus R dt, right? So 1 plus R dt should be even like more familiar to you, right? It's kind of the same plus R dt is a percentage, right? And this is exactly the state, the savings for tomorrow, right? It's always comparatively tough to just remember when you should put dt, when you shouldn't put dt. Because for instance, for your saving, you shouldn't put dt because it's like something accumulates. It's kind of a stock variable, and your consumption is kind of a flow variable. And let us first operate with this and kind of master these operations with dt first. So what we naturally always want to do, we want to linearize everything in terms of, well, small variables, that is dt. So let us do this. So the first approximation is for this, right? It's 1 plus r dt up to the first order. Remember, always only up to the first order. This like that. Then we just can open brackets. And what do you see here? It's kind of, we'll have st. Here we will have summands of the first order, and the final one will be of dt square, right? And remember, dt square according to our rules is 0, right? So when we open the brackets first, it's like that, but we can cancel out this one, and eventually it's like that. So you always do something like that in continuous time. You can first write as it is, like actually, and then you can always like apply the first order approximations and the rule that dt square is equal to 0. And then you will arrive to the actual, what's called evolution of the state variable. So you can see here, it's actually quite, straightforward how to read it, right? Your savings, like in the next instant, is equal to the same savings that you had, and the changes to this savings is actually your consumption, right? For this infinitely small time period dt, right? And your actually percentage on your savings, right? Here it was like that you have like, second order effect, right? Because you consumed something and only then you take percentages, right? But you consumed infinitesimally small and the percentages are also infinitesimally small, right? So you neglect this second order effect here. So it's kind of straightforward how to read it here. And now finally, let us formalize, the value function, right, for continuous time. It's the same as we had before, but now it's not as a sum, it's an integral, right, because the time is continuous. And otherwise, it's absolutely the same. So again, when you're at state st, we start with time t, and kind of instantly you do not discount your current utility, right? But then you discount them at higher and higher rate, right? And again, what we do to write a Bellman equation, we represent this value function. Remember, in discrete time, we just plug out the first term, right? Exactly, which is for time t, and then the remaining terms. Here, there is no next instant, right? We cannot plug just something and write additional terms. So what do we do, right? We just decompose it into two. So it's like from like today t to t plus dt. So it's like an infinitely small term basically here, right? And all the remaining terms. So it's the sum from t plus dt to plus infinity. And here we plug out the discount rate for exactly, from t to t plus dt, right? And what do you see here? Again, if you just look at this expression, it will be exactly v from st plus dt, right? So it's a value function from the moment t plus dt, right? Because it's absolutely the same expression as you see here, right? And here is basically, again, the discount rate. Remember that before it was beta, right? Now it's just this discount rate. And the first term is kind of your instantaneous utility. And here we can actually simplify, right? So you see here, it's from t to t plus dt, right? So it's almost a zero kind of length of an interval of an integration, right? So when dt approaches 0, it will collapse to 0 actually, right? But remember that we're interested in something up to the first order of, of dt, right? And actually, there are some math theorems like the mean theorem, probably how it's called, right? That, in this small time increment, this function under the integral, it almost stays the same, right? You know, it's kind of a continuous function, right? So it's almost like the same. So it's almost like a constant. And the interval of integration is dt, right? So when you collapse dt to 0, the argument here, it collapses to just some particular numerical value evaluated exactly at point t, right? And the length is kind of proportional to dt, right? It's just dt. And therefore, you know, with some rigorous analysis, you can show that actually the first term, right? It's just exactly, you know, when you substitute tau equal to t, it's 1, right? So it's a ln of ct, and dt is the length of integration. So eventually, the Bellman equation will be like that. You can skip this argument of decomposition, right? Because it's always the same. And just from the start, write that Bellman equation in continuous time, which is called Hamilton-Bellman Jacobi, HGB, Hamilton-Jacobi-Bellman equation, is like that, right? So the logic is absolutely the same as in discrete time. So that your value function today is equal to like your instantaneous utility, right? And now, you know, the time increment is dt, it's not 1, right? So it's not exactly your utility from today. It's like your utility in infinitesimally small time period. And then starting from, you know, t plus dt, right, which you discount by this, you have, again, the value function that is you act optimally starting from t plus dt, right? So basically it's the same, but now kind of, you know, instead of time increment of 1, right, where you have utility function for 1 period and then you discount the next one, and then you start with value function of st plus 1. Basically, instead of once, you all the time substitute dt in free time. Any questions regarding this analogous to Bellman equation in continuous time? Okay, so let us finish with the Ramsey model in continuous time. And remember that what we had is an evolution of the state variable, right? Which we found here, right? And this is exactly the Bellman equation. As I said, in continuous time, it has some separate name, HGB equation, but you know, no one cares, and always it's just again a Bellman equation. And actually, the algorithm is absolutely the same. So you just substitute this state evolution of state variable, so the state at the next instant, into this argument of the value function, and then you do what I promised, like you do Taylor approximations. So let us do this, and let us prepare ourselves. Here, you know, the calculations are quite long, but they are at the same time quite straightforward, because almost always nothing cancels out. So you just substitute long expressions into other long expressions, and that's it. You know, just don't be scared to do this. So let us see. Here you already have something linear in dt, so it's fine. Here we will again use like first order approximation. It's 1 minus r dt, right, up to the first order. And here, if you substitute this particular evolution, right, you will have that, according again to the Taylor rule, that v of st plus dt will be equal to v of st, right? And here you have infinitesimally small, right, like small change in the state variable. So up to the first order again, this term will be again this change, right, multiplied by v prime, again evaluated as st, right? That's just the Taylor rule expression for this, right, using this equation. right? And so what do you see here, right? Here it's linear, here it will be linear, and this one again, it's linear, right, in dt. So again, when we'll multiply these two, again, we will have terms of order dt square, which will cancel out. So our goal is basically to have in the right-hand side something of order 0 in dt and order 1 in dt, and that's it. And let us do it. So eventually, when you multiply these two, when you approximate them with the first order approximations like here, what you will eventually have when you multiply these two is like that. As promised, this term, which is quadratic in dt, doesn't participate here. So here, when you multiply like basically 4 numbers, right, you don't have 4 terms, you just have 3 terms. It's kind of puzzling, but it's how it is in this word. And so you see here, right? So as promised, so it will be again v of st. So basically it will be the same value function here, right, as it is in the left-hand side, plus again some marginal changes. And let us substitute into here. So here is just exactly this expression, right? And what do you see here? Next is just, something that always happens, and with that you can always check that you're on the right path, is that v of st has to cancel out. That is, in the left-hand side and in the right-hand side should be the terms of order 0 in dt, right? Exactly this value function, and they have to cancel out. So everything that should remain should be of order dt, right? So everything of the 0 order in dt should cancel out. So I just cancel it out, and what remains is like that. And then I can cancel out dt, right? No matter that it's infinitesimal small, remember it's strictly positive, so I can cancel it out. So I just cancel it out, and eventually I arrive to something like that. That's again kind of a Bellman equation. You can write it in more natural way, for instance, transferring this term in the left-hand side, and because it doesn't depend on CT directly, right? But even in this form, it's fine, right? So how we can proceed with solving it? First, again, it's like the maximum of CT, we can take the first order conditions, right? And when we just take them, we will result into this, because here it's 1 over CT and here it's minus V prime. And also the Bellman equation itself, right? Because, we need to find exactly optimal CTs, right? And therefore, we can just write that when CT is exactly optimal, right, we have that this equation is satisfied. Right? That is when these CT are exactly maximized. And again, we just arrive to some system of equation. And here, it's not just a system of equation, it's a system of differential equations, right? So as promised, it's kind of a wild west after you write Bellman equation. So there is no generic algorithm of how to do this. And here you arrive to a system of differential equation. And again, luckily, it turns out that for this particular case, it's solvable, and you can solve. And eventually you arrive to that the value function is equal to this. So just some constant plus log of st divided again by some constant. And from the first equation, then you find a particular, how it's called, policy function. That is, your consumption is always a share of your savings. But that is irrelevant, actually. Everything that is after writing a Bellman equation, basically after this stage in continuous time, right, is kind of irrelevant, because I'm for sure not interested in kind of actual solutions, because they are all the time different, and we are not exactly interested in Ramsey model. And also, I'm not that much interested in this particular, let's say, system of equation, because as I said, there is no generic algorithm of how to do this. And in our models, it will be kind of different, right? Therefore, it's quite useless to memorize any kind of ways how to solve this exact problem. All in all, it's just, just to show you that the convenience of continuous time. That is, it turned out that because the state variable doesn't change too much, we can apply Taylor rule approximation, right? And instead of difference equation, that is the value function evaluated at a different point, right? We could transform it into the same value function, right? And cancel it out, and therefore transform it into basically a differential equation, and whereas the argument will be the same for the value function. And this is much, much easier. That's it with dynamic programming. And in the remaining time, I will briefly outline you the stochastic processes that we will need to use. So in general, it's a super broad topic. You can have like yearly courses into this, but we will need just two: the Brownian motion and the Poisson process, and both are used small information flows in continuous time, right? And why are they popular? Because they are just particularly simple to operate with. So first, let me outline the Poisson process. So again, let us assume that we're in continuous time with infinite horizon, and Poisson process, it's kind of a count process, right? So the time starts from 0, and then it goes on, and at some stochastic moment, some events occur, right? And this event basically adds 1 to the counter, right? So initially your counter is at 0, and then at some random point in time event happens, your counter increased by 1, so it's 1. Then again, time went on, and then again at some point in time event occurs, this adds to the counter and so on, right? So basically at any point in time, the state of this process is just some natural number, that is the number of events up to this moment in time, right? And clearly we can define slightly different object, right? Because we started at point 0, right? Then we can have 2 points in time, right? B and A. These are some times, B and A. And then we can calculate the number of events from 0 to A and from 0 to B, right? And this difference will give us the number of events from A to B, right? And so like here, I just outlined that, in some random times, the counter adds by 1. And here we exactly specify like how it happens. This probability distribution of this arrival times of event. And we specify it such that exactly the probability that within time interval from A to B, K events happen is equal to this, right? Actually, you can calculate that if you sum up these probabilities for different Ks, right, from 0, 1, 2, and so on, plus infinity, right? So you have an infinite sum over Ks, you will have 1. That is, it's indeed a probability function, right? And you can actually show it because here, if you look at these terms, it's exactly the Taylor rule or term for the exponent, for exactly this exponent, right? And when and this is a constant, right? It doesn't depend on K. And when you sum up these terms in K, you basically sum up infinite Taylor rule series for the exponent, right? And when you have this exponent, when you multiply by exponent with this minus power, right? You're right. So it's indeed a probability function. Here, actually, I have a correctness check that I won't go into details here, is that, to check that, it's a correctly defined distribution, you actually need to check that, for instance, you have some time period, right? Let's say from A to C. And you can divide it with some B into time periods from A to B and from B to C, right? And you have that from A to B, you have some probability distribution on how many events can happen here. And from B to C, you also have defined here as a probability distribution on how many events can happen there, right? And clearly that this defines you, right, just from the definition from A to B and from B to C, it induces you some particular distribution of the number of arrival times from A to C, right? It's just exactly like that, right? If from A to B you had some I events, and from B to C you have K minus I events, so in total you had K events from A to C, right? And therefore the probability that you exactly have K events from A to C is this sum, right? And here the probability distribution, here and therefore you can explicitly calculate the probability distribution for the interval from A to C. And it turns out that when you do this sum, right, it will result into exactly the same probability function as you had here with the needed numbers, with the needed endpoints for the intervals. And that means that the definition is correct, right? That is, when you induce the probability distribution on some intervals, right, then it's correctly defined, right? That is, the distribution for the whole interval will basically be correctly defined with the same formula, right? Irrespective of how you divide this interval into sub-intervals. All in all, here it's correctness check. But what is important for us about these properties of this process is the following. That is, first is what is called memory loss. That is, if you had some number of events up to the point A in time, right? The number of events from A to B, right? That is from this point onwards, it doesn't depend on what was before, right? It's directly incurred from the definition, right? Because the number of events from A to some upper point B, it depends only on the endpoints A and B, right? It does not depend on what was before A, right? Nothing before A enters here. Nothing about previous counter or whatever. Second, here is just, the number of events within this time period from A to B has, actually this density, this probability function is a Poisson probability, right? So here it's the Poisson probability with parameter lambda times B minus A, right? So what is important here is that basically the larger is your interval, right? The higher is the parameter of this Poisson distribution, like linearly high, right? And when you calculate the expected number of events within period A to B, it will be equal to exactly this parameter of this Poisson distribution. You can find it in Wikipedia even. And what will be particularly important for us, basically the only thing that will be important for us about it, is that, again, remember, we will operate in continuous time with, again, these infinitesimally small changes in dt, right? And therefore, when we will have a time period of length dt, which is small, right? The probability to have k events within this period of dt will be equal to lambda. Here it's dt times k, e to the power of minus lambda. Here it will be dt divided by k factorial, right? Something that I wrote here. And as you see here, when k is equal to 2 or 3 or whatever, right, according to our rules that dt square is 0, right? It will be 0. That is, it will be possible that either you have like 0 events, right? Then k equal to 0. Or just one event within time period of length dt. And this is the only thing that will be relevant for us. So here it's exactly what is written here. But we will need it just once and probably like in 3 or 4 lectures from today. And Brownian motion. Brownian motion is kind of entertaining, but again, it's more complicated. So first I want to show you the random walk, which is the discrete time analog of Brownian motion. So it's like you have again from 0 to plus infinity continuous time, and you have some starting point on y-axis, right? And denoted just x0. And here you have first again for random walk it's discrete time. Sorry. So in 0 it's x0, and then in the next period, all the time, the value of this process is like that. That is, it just takes the previous value of this process, adds some fixed number a, positive, negative, whatever, and then just some random noise, right? So that is some random variable which is distributed as normal with 0 mean and some variance sigma squared. Here I wrote like sigma times standard normal distribution. So it's like that, for instance, right? So you have some deterministic change in parameter of xt and some kind of unpredictable change in xt. And then again, it's like at t equal to 2, it's like that, and so on, right? So it's basically some sequence of dots. And what is Brownian motion? We just take the same formula as we had here, but apply it to continuous time. And we do application to continuous time in absolutely the same way as we transform the Bellman equation from discrete time to continuous time. Right, so again, we just substitute all ones with dt's, right, basically. So again, now the time is continuous, and again, there is some starting point for the process. And then in the very next instant, xt plus dt is equal to the previous value of xt plus some deterministic change, right? It's like a times dt, that is within dt, the slope is like approximately a, plus again some unpredictable part. And here unpredictable part is again normally distributed random variable. Again, sigma is the variance basically. And here what is important, the variance of this unpredictable part is exactly dt. Not dt squared, not the square root of dt, it's exactly dt. That's important actually. And within this representation, A is called the drift term, right? It's kind of a trend. It's kind of deterministic part of the movement of your variable. And sigma is the variance, that is kind of volatility, right? How volatile is the change? For instance, you know, for these equations, you can apply any stocks, any oil prices, let's say, whatever. They are all believed, all prices are believed to follow Brownian motions, right? You have some predictable component in the movements and you have some unpredictable components. And again, just, you know, in continuous time, what is a Brownian motion? It's just kind of, we approach this dt to 0, right? And look at how this continuous process. So for instance, it's just how this was generated in later, right? Something like that. So it's a particular example of a passive Brownian motion. It just takes some and then goes unpredictably. I don't know what trend it is, probably something like here. What is important about Brownian motion? First, it's kind of more convenient a bit to write it in differential form, right? so that to transfer this xt to the left-hand side, right? And write it in the fact that the change in xt, right, is equal to the predictable change and unpredictable change. And finally, as a final piece for the lecture today, I wanted to outline the basic properties again that we will use. That is, suppose you are at time t, right? So you are today, and you want to kind of have some predictions about the change of this Brownian motion, right? So how it will change tomorrow. That is, you know the current price of some stock and you want to predict like what will happen tomorrow with this stock. And here is quite straightforward and just, very basic calculations. And the expected change is clearly equal to A times dt, because this one, it's a random variable, first of all, but it has zero mean, right? And therefore, when you just apply expectation, it's linear, right? So expectation of this, it's deterministic, it's a constant, right? So it's A times dt, and expectation of this is 0. So the expected change is A times dt. The variance of the change is vice versa, it's sigma squared times dt. Here it's marginally more complicated to derive, but when you take the variance out of it, this is, again, it's a deterministic part, it's a constant, right? It has no variance, it's 0. Something wrong happened, but okay, let's see what will result in. So I proceed with the variance. So the variance of this part is 0, and the variance here is actually, it's variance equal to dt, right? And when you multiply by some constant, the variance becomes sigma squared times dt. And finally, what will be also important, the expectation of the square of the change, right? We will actually also use it. And here we will just apply the formula for the variance, right? Because the expectation of the square is equal to the variance plus the squared expectation, right? And actually, we just apply it here. So the variance is equal to sigma squared times dt. And this one is equal to then a squared times dt squared. And again, remember that dt squared is equal to 0 according to our rules. And therefore, this term vanishes. So actually, it's 0. And what remains is just like that. So that's finally it. That's a long lecture, but it's an introductory one for future short lectures. So what we studied today is just a collection of mathematical methods. So exact problems that, for example, will not be exam relevant or whatever, but they, provide you with some flavor of how these dynamic methods look like. So how you can solve dynamic problems. And we discussed like basic principles of writing Bellman equation in discrete and continuous time. And, what is common about all problems is other steps for writing Bellman equation. So when you just write Bellman equation and derive the evolution of the state variable, it's always the same for any problem. But how you solve the resulting Bellman equation, it's completely, up to you, basically, how you manage to do this. And also we discussed some stochastic processes which will be relevant for us. We'll use them into some models, and we won't need that much from these processes, but basically just some properties that I outlined you today. So that's it for today. Hope the lecture recorded well, but I'm not sure right now. So we'll see. So thank you and see you on Saturday when we'll begin our first model. It will be discrete time-bound equation model. So thank you, and that's it.